Another application of net change is displacement. If an object moves along a straight line, this is rectilinear motion, according to the position function s of t at time t, then its velocity, of course, is the derivative of the position equation. So I can write a definite integral that says this. I got a definite integral over the time interval from t sub 1 to t sub 2 of our velocity equation is equal to the change in position that I have over here. This is our final position minus our initial position. This is called displacement. It's not the same thing as the total distance an object travels. It's a net change in position, our final position minus our initial position. It's entirely possible that an object travels, let's say a mile, but its displacement, its net change in position, is zero, as in it started and ended at exactly the same point. Here's an example. Let's say that I'm throwing and catching a ball straight up. I throw a ball up and I catch it at that exact same height. I can think of this as a positive distance, and then coming straight back down as a negative distance, which cancels each other out. I end up at the exact same location. It has a displacement of nothing, even though it may have traveled, this ball may have traveled a couple of feet. Okay. All right, so I'm going to rewrite this equation, just rearrange it just a little bit, knowing that s of t sub 1 is our initial position, s of t sub 2 is going to be our final position, and sometimes what we do is that we add this s of t sub 1 to the other side of the equation to get s of t sub 2 is our final position is equal to s of t sub 1, which is our initial position, plus some kind of change in position. Okay, we're going to use this kind of equation here on our next example. All right, it's going to seem a little bit familiar to you because we've seen it before on a quiz, but I had to take off part D because it involved integrals, and I replaced it with that local linear approximation. The figure at the left shows the graph of f prime, the derivative of a twice differentiable function f on the closed interval from -3 to 4. They mention that it's twice differentiable because the original equation has a derivative called f prime, which is graphed here, and then you have to be able to take its derivative in order to find things about it like concavity and points of inflection. The graph of f prime has horizontal tangents at -1, at 1, and at 3, and remember, that's where those points of inflection were. This is the new part of this. The area of the regions bound by the x-axis in the graph of f prime on the intervals from -2 to 1 and 1 to 4 are 9 and 12 respectively. So that's going to come into play for the part of the question that we're going to answer right over here. Given that f of 1 is equal to 3, write an expression for f of x that involves an integral, and then find f of 4 and f of -2. Now, you might be looking at this going, well, what does that have to do with the displacement thing that we were just talking about? Well, one of the things that we can think of this as is we can think of this as our velocity equation. This is s prime of t, right? Our velocity equation. And then when we find this f of x, we're actually finding our position equation, and f of 4 and f of 4 and f of -2 is just simply going to be our position at these particular times, taking this initial position into account. Okay, so let's start by writing ourselves some sort of integral expression involving this f prime business. So one of the things that I absolutely need to start with is our initial time. I'm starting with the initial, that makes sense. So this a that's right here, that's this a. How about this 1 that's right here is going to be our a. Our a is equal to 1. It's our lower bound. And this x, since we want an expression from the initial position to some time x, that's going to be our b. So our b, come on, write this. B is equal to x. There we go. All right. So our integral expression is going to look like this. I'm going to take the definite integral from 1, our starting place, to some time x is equal to f prime of x dx. Oh, wait a minute. Notice I have an x here, and then I also have an x here. So if this changes, this also changes. I don't want that to happen. I need a different variable for either the upper bound or what I plug in here. This one needs to stay because that's the one that we're changing, which means I need to go back to this integral expression and then change that to some other value, which is commonly just a t, but you can pick whatever you want as long as it's not this x that's up here. Okay, so follow me here. This should be equal to the antiderivative of f prime of t is f of t. And we would be evaluating that from 1 to x. So using the fundamental theorem of calculus here, I'm going to bring this integral expression down. It should be equal to f of x minus our f of 1. So remember, just like I was explaining before, you can think of this as the definite integral of some velocity equation, and then this is going to give us our change in position, our displacement, where this is our final position, and here's our initial position. I'm going to go ahead and add this f of 1 to the other side. I would recommend, highly recommend, that this is the way you tackle one of these problems. Start with the fundamental theorem of calculus, apply it, and then rearrange your equation as needed. So I would have f of x, which is the equation that we're looking for, is equal to f of 1, our initial position, plus a change in position from 1 to x of f prime of t dt. There's one last thing to do for this, and that is to take out this f of 1 and put our actual initial value of 3 here. It tells us that f of 1 is equal to 3. So I'm just going to erase this and then put 3 in its place with a laser. All right, so this is the first part of that question. It asked us for an integral equation for f of x. We've got it. Okay, so now we want to find the value of f of 4 and f of negative 2. F of 4 should be equal to this initial value plus the change from 1 to 4 of f prime of t dt. All right, well, this part's obvious. That's right there, scribble, scribble, but this part maybe not so much. How am I supposed to get the value of this definite integral from 1 to 4 of f prime of t if I don't have an equation to take the antiderivative of this and plug these values in? Well, remember that this thing that's right here, this definite integral, is just area from t equals 1 to t equals 4. And where am I going to get that area? I'm going to get that from the graph. Let's go back to the graph that's right here, and let's do a little bit of coloring. Let's say I choose green, because this part that's over here, they said the area is a 9. So that part's a 9, and then maybe change the color here to a blue, and the area over here is supposed to be a 12. And that's the one that we want because it says we want the definite integral from 1 to 4. We want the area of this curve from 1 to 4. So this should be equal to 3 plus 12, right? Except no, that's wrong. Why is it wrong? It's wrong because this is under the x-axis, so this should actually be a negative number, and that should also be a negative 9. So I need to make this a minus 12 for a total of negative 9. So here we have the answer, f of 4 is equal to negative 9. Boop. All right, let's do this one more for f of negative 2. Yes, f of negative 2. Well, that should be equal to our 3, our initial again. Change from 1 to negative 2? That's weird, f prime of t dt. Why is it weird? Because the smaller number is up top. Well, if the smaller number is up top, then that means that this integral is improper. We got to put the smaller number down here. So we can do that pretty easily as long as we switch the sign out here. So this is going to be equal to 3 minus the definite integral from negative 2 to 1 of f prime of t dt. And then once again, this part is going to be interpreted as area on the closed interval from negative 2 to 1. And I'm pretty sure we have that from the picture. We said that that is a negative 9 right there. All right, low battery. Well, that's okay. I'm almost done with this one. So this should be equal to a 3 minus the negative 9 from that area. The negatives cancel out, and I get a positive 12 here. So f of negative 2 is equal to 12.